Just wanted to welcome everyone to our contested space, Automating SDA Testing and Training webinar, hosted by AI Solutions and the Free Flyer team. Thank you all for joining us. Now, just wanted to introduce myself. I'm going to be your moderator for today. My name is Christopher Ulrich. I am the Space Products Account Executive here at AI Solutions for the Free Flyer team. I'm also going to be joined today by Danny Brown, who's in attendance here. He is also a Space Products Account Executive, and he will be monitoring our Q&A at the end of this webinar. So please make sure you stick around for that. And we also have some other information about upcoming events later this year towards the end of the presentation as well. All right, so we definitely have an exciting presentation today for everyone. It's going to be led by our very own Stephen Paligo, and he's going to take us through an introduction, to AI Solutions' new ObsSIM product. This is an industry leader in testing, training, and automation simulation exercise needs, particularly for high quality space-based observations. Stephen, if we can jump to the next slide without further delay, I will turn the presentation over to Stephen to introduce himself and his extensive background. Stephen, take it away if you would.
All right, thanks. So yeah, just a little bit about me. I'm Stephen Paligo. I am the Joint Commercial Operations Training and Analysis Lead for AI Solutions. I've been working in the realms of space situational awareness and space domain awareness for about 14 years. During that time, I've worked on a variety of interesting projects, some of which are machine learning for space event detection. I worked on a large-scale space surveillance sensor, getting that created and deployed, as well as space domain awareness, data processing, specifically in the realms of launch data and satellite breakup data. But my current focus today is on SDA operator training and space data quality. And that's enough about me. Let's get into the good stuff. So in the past, we relied on space situational awareness. That was the environment we worked in. Specifically, space situational awareness is just maintaining a catalog of satellite states in order to prevent accidents from disrupting mission. Specifically and primarily collisions. We were doing collision avoidance. We didn't want things to run into each other. But we're not operating in that environment any longer. The military space environment is now congested, it's contested and competitive. So in the past, we had to prevent from accidents. Now we have to prevent from adversarial, hostile actions. So in the past, we'd see a launch and we would need to verify that nothing was going to get hit during the flyout or in its initial orbit, that there would be no collisions. Well, no longer can we just do that. For example, with a launch, where is it going? There are nations that intentionally try to evade space surveillance sensors and fly in the dark, as it were. And so we have to ask, well, what is there a nefarious purpose behind that? For example, is it an anti-satellite weapons test? For things like rendezvous and proximity operations, you have a chaser spacecraft coming into proximity for your high-value asset. What is it doing there? Is it just going to park nearby and be benign, or is it going to have some other hostile intentions? For example, it could be eavesdropping, or here I'm showing a circumnavigation. Is it going to begin circling around my high value asset for intelligence or eavesdropping purposes? And then is my target is my high value asset a target for hostile actions, such that we have to be aware of things like collisions from kinetic kill vehicles or something similar. So no longer can we operate assuming space is benign, but we have to operate as if they're hostile intentions. We have to change a paradigm, move out of SSA and into something else. And that new paradigm is space domain awareness, which is the identification, characterization, and understanding of factors associated with the space domain that affect space operations. Because our societies are so reliant on assets in space, any impact to their operation can affect the security, safety, economy, or the environment of our nation. Now, although this quote is from someone representing the United States, it's applicable to all nations with assets in space. Those with adversaries looking to harm them, or other assets that might be collateral damage if hostile actions took place. So this is an issue that everyone should be concerned about. So in real operations, we don't have an omniscient view of what's going on. Are there hostile actions? We don't know. We have to figure it out. Unfortunately, we don't have a 3D visualization of everything that's going on, looking through from the past through to the present into the future. What we have to do is build that up from sensor observations. So this raw data that we get from space surveillance sensors needs to be brought in and turned into that omniscient view. And in fact, space surveillance sensor observations are the primary initial indicators of adversary actions. So it's really important that we start with that as first conditions and build up to the omniscient view to understand and have an awareness of the space domain. And in order to do that and move through that process, SDA operators, they need advanced training to detect and to respond to adversary actions, some of which may be novel, not seen before, and they need to do so using the data and software that they would in a real conflict. It doesn't help to train on data that isn't representative of reality, or tools that they wouldn't have in a real conflict. And then take this training and use it to practice and refine the tactics, techniques, and procedures of what they would do in a real conflict. So if you are designing an SDA exercise for test or training, given that the observations are the most important part, they're the initial conditions, the initial indicators of hostile actions, that begs the question, where do we actually get that data? And it depends on the exercise type. So there are a number of common exercise types seen today. The first of which is called a tabletop exercise. And in that, participants sit around a table and discuss the threats and actions they would take in response to those threats. So exercise organizers would hand them inputs either verbally or through what's called a white card, where information is written down and handed to the participant, and then they're expected to formulate a plan and react to that. That system has some benefit to it. It's really easy to organize and execute that kind of exercise. It's also really flexible. Anything you can write on a card can be an input to the participant. Unfortunately, it comes with some significant drawbacks. So participants, when they participate in a tabletop exercise, likely don't interact with real systems or data. Everything is fed to them. So it lacks a certain realism that they would have in an actual conflict. And then it's easy to gloss over important details. Participants may assume that they have information available that they don't actually have, or that it's easy to implement a procedure, some course of action that they take, and the details are a lot more difficult to actually do. Another type of exercise is the playback of historical observations. And for this, exercise designers, they find historical sensor observations and play them back into tools that the participants use. So they find real data sets and provide those to the users. And this has the benefit of realism. These are real data sets. So they're real observations of real spacecraft in a real space environment. So you get the benefit of realism, but again, it has some drawbacks. It's often hard to obtain these data sets. So you may, as an exercise designer, have to go in and scour different systems and talk to different people. And if the data is not cataloged the way you need it, just getting it and filtering it from everything else is really difficult. Secondly, classification issues often arise. So data sets with the highest training value often are classified and so unable to be shared, for example, with other participants from allied nations or other groups that you would normally interact with. If there are security barriers there, that data often can't be shared. And then trainees are limited to the courses of action that actually occurred in the data. The data that's being played back as a historical record of the thing that happened, the one thing. There are no alternate courses of action. So if an exercise participant says, I would do this differently, they don't have the data to exercise with for that alternate procedure. And then a third type of exercise we often see is the use of pre-generated synthetic data. So in this type of exercise, the designers, they build data sets and then they're synthetic, so it's fake data. But they build these data sets to specifically accomplish training objectives for their exercise. And this has the benefit of being customized to exactly what's needed. There's no need to search for data, and you can often get around classification issues because the data is not real. So before the exercise, they generate whatever data that they think will be needed and then play that to the users through their tools or other means during the course of the exercise. The downside to this is that preparation for these exercises requires great skill and time. There's one exercise, I won't specify which, but one exercise that gets run yearly, large-scale exercise involving many nations, and data is generated immediately after the exercise ends. They start and spend a year generating data for the next exercise. So it requires a lot of time and then skill to actually do that in a realistic way. And then trainees are limited to just the courses of action that were dreamt up by the exercise designers. So if they want to come up with something new and novel, you have the same problem as with the historical playback. The data just isn't there because nothing was generated for that novel course of action. So what do we do about that? Well, there's a better way, and that way is to automate the synthetic data generation. Okay, we've hypothesized that by doing that, you get the benefits from the previous exercise methodology, but then it's also easier and quicker to design the exercise because it's automated. And if you can generate that data quickly, it allows the exercise designers to generate new data as different courses of actions are explored. So to test that hypothesis, what we did was we built such a system. It's called ObsSIM, which is a high fidelity real-time observation simulator for these tests and exercises. And then over the course of the last over 4 years, we've been using it and refining it and iterating on that system to as we generate exercise data for various users. So first, I'm going to talk about how we built this system, kind of how it's structured, and then share some lessons that we learned from doing that that can be taken into exercise design as you embark down that process. So ObsSIM, the fundamental building block on which ObsSIM is made is FreeFlyer, which is the AI solution commercial tool for satellite mission design and analysis. It's a product off the shelf that has a technology readiness level of 9, so very mature product, and indeed has been used over its 27 years to support hundreds of satellite missions and dozens of ground systems. And it's in use by civil, commercial, military, and academic organizations worldwide. So on top of FreeFlyer, we have ObsSIM, which is structured in general as a library of events and sensor models. So event models and sensor models. And in order to generate space surveillance observations, we need spacecraft event models to generate kind of the ground truth from which the obs are made. So first, we support a number of event models. So here's a list of the categories, broadly speaking, that we support. So launches, we're talking normal satellite launches, as well as anti-satellite weapons tests, breakups, think collisions or explosions that occur, rendezvous and proximity operations. That's anything that gets up close to a target spacecraft. For example, a natural motion circumnavigation or a forced motion circumnavigation. Those types of things fall under the category of rendezvous and prox ops. Re-entries, both controlled and uncontrolled. Close approaches, common maneuvers like station keepings, plane changes, injections to geo, that kind of thing. Common maneuvers are also included in there. And so we use these event models to build a sequence of events, and that becomes, as I said, the ground truth from which the observations are generated. So the observations are made by our sensor models, which include radar, electro-optical, and passive RF models, both ground-based and space-based. And here you can see a map of the sensors currently in operation in our system. So you can see they span worldwide. We have both commercial networks, military networks, and are able to simulate those realistically and generate observations from the ground truth that's produced by the event models. So back to FreeFlyer for a minute. So in order to build these event models and these sensor models, we've leveraged a number of FreeFlyer features. To build the events, we use GP and ST propagation. So we build, as I said, a sequence of events, propagate between them, and then use FreeFlyer's maneuver modeling, as well as its targeting and optimization, to dial in those events into exactly what the exercise requires. And then we can validate those with FreeFlyer's 2D and 3D visualizations. So ensure that the events that have been modeled meet the exercise objectives. And then after that, in the process, we have sensor models that try to satisfy sensor tasking. There's a real sensor tasking algorithm. So we use FreeFlyer's coverage and contact analysis to do that, to generate path schedules when the sensors will see the targets and have opportunities to collect observations on them. And then use FreeFlyer's observation modeling to generate the observations during those pastimes. And then we can also use FreeFlyer's orbit determination to generate state vectors off of the observations and maintain a catalog built up from the simulated noisy observations that mimic the catalog maintenance process that happens in real life. And all of this is done through FreeFlyer's runtime API, So there is, as I said, it's automated. So everything is machine to machine. We can generate these events and simulate the observations without a human in the loop, all because FreeFlyer offers this API to accept inputs in and then pass data products out of its modeling. And so FreeFlyer really gives us a solid base of out-of-the-box astrodynamic tools on which we could build ObsSIM. So next, I'll talk about kind of the workflow that one would go through to use ObsSIM or a similar observation generation capability to design an exercise. So first, we start out with an event model. As I said, breakups, launches, RPOs, etc. We have these library of event models with which a user can generate an instantiation of that event by giving it a configuration. So for example, a launch, we would need a launch time and a launch site, an azimuth, etc. And so the user passes those configuration parameters to an event model and generates the ground truth data. From this, the user can customize the exercise to fit their needs. So maybe they need to iterate on the ground truth data, regenerating it multiple times with different configuration parameters to ensure that it fits the exercise needs. And once they get that in a good place, they can augment that ground truth data with other models to augment realism. So for example, spacecraft attitude or visual magnitude modeling, those get layered on top of the ground truth positional data. And then the user takes that ground truth and schedules the execution. So as I said, FreeFlyer is a real-time system. So it can generate data in real time, meaning that the exercise designer puts in the truth data, and then obs get generated at a realistic cadence from that. And by operating in real time, it allows the system to respond to participants' actions. So if a exercise participant wants to, for example, move their spacecraft away from an aggressor, they can add in a new state for that, generate a new orbit, and that gets put in and is reflected in the observations. Since they aren't pre-generated ahead of time, they can be changed at a moment's notice. So that ground truth is scheduled for execution, and we get the real-time sensor observations. Those observations are then pushed to a variety of data destinations depending on the exercise needs. So that might be a data repository for the exercise. It could be a sim over live system, which merges simulated data with live data in such a way that whoever's consuming that data does not know what is the sim and what is the live, and taking away any aspects of cheating or making different decisions because you know something is simulated. And then from those systems, the data is pushed to the operator's actual tools so that they can train as they would act in normal operations. And then over time, as I said, users are able to modify and extend the simulation in real time. If they want to maneuver a spacecraft in response to something, then they can send that into the system, and then the observations will be made of the updated states. So here's an example of configuring a breakup event. So on the left, you see a set of simple inputs: the start and end time for the event, the satellite that's going to break up. We have delta V parameters for the pieces, a breakup time, and then a number of pieces. So with a small number of inputs, a user is able to create the event that you see at the right, an explosion of a spacecraft. So now that I've talked about what ObsSIM is and how it works, let's go into some best practices, things that we've learned as we've designed space events for these training exercises. And so I have 10 best practices to share. And the first is related to the events. So first, you need off-the-shelf event models. As I said, to automate the OBS, you need something to be observed. And so such a system needs to provide off-the-shelf event models, breakups, launches, common maneuvers, etc. And then we found it's often useful to the exercise designer to have a library of pre-made events that they can draw from to run at the times that they actually ran, or maybe to advance in time to overlay other events that they've generated. Here you see an animation of a recent launch of the Chinese space plane. And having something like this off the shelf, or for example, the Russian anti-satellite weapons test that happened a few years ago, provides immense training value, and it prevents the exercise designer from having to go get the event parameters themselves. So by providing canned events, pre-made events of significant interest, allows them to easily create an exercise event with little to no effort. And the third best practice is the ability for exercise designers to import external event ephemerides. So if they have, for example, data that they have collected that they want to use, or they were able to mock up an event in an external tool like FreeFlyer, or some other high fidelity event model, allow them to bring that in. So by providing these three capabilities, a system would allow maximum flexibility. So models that already exist, pre-made events that already exist, and the ability to bring in external data that already exists. All three of these allow great flexibility to exercise designers for creating space events. And then finally, from all of those, provide visualizations and reports for them to validate that their events, from whatever source they came from, look as they do. Here in this example, you see that the Chinese space plane flew through several sensor coverages. That's what those cones are sensor coverages. And perhaps an event designer needs observations to occur at a certain time. Having visualizations and reports and plots allow them to validate those constraints and ensure that what they designed, regardless of the source, meets the needs that they have. Next, we'll talk about best practices of sensors. So again, similar to the event, we need off-the-shelf sensor models. There's no point in automating this process if the user has to build up these models themselves. So having off-the-shelf models of sensors with different phenomenologies, so radar, passive RF, electro-optical, etc., space-based, ground-based, different locations, having these off-the-shelf sensor models gives them the flexibility to create observations very quickly without having to create the models themselves. And then again, a library of real sensors. So to save the exercise designer from having to go and gather all the parameterizations for those sensors, have a library of real sensor networks, commercial, military, et cetera, that they can draw from to generate their exercises. And that greatly speeds up the time between design and execution. And then third, to allow maximum flexibility to give the exercise designers the ability to import externally generated observations. They might have access to a high fidelity sensor model or data that's been pre-generated that they want to use in their exercise, giving them the ability to bring that in instead of generating it in real time. And that allows for maximum flexibility. And then the last three best practices revolve around data. So exercise designers need to be able to get that data out to the users. So a best practice of an automated observation generator is to have great flexibility in publishing that data. So to different sources or to different destinations like the Unified Data Library, or perhaps Kafka topics or file drops or databases, those kinds of things. And then in a variety of formats, think JSON and protobuf and CSV files. You can follow the CCSDS formats. Having all of those in a support for a large variety gives maximum flexibility to exercise designers. The next is role-based access to that data that is produced. So if there's a certain type of exercise called red versus blue, where you have teams playing against each other and they have limited sets of information, just as different groups in real life would have access to different information. So being able to segregate data to a group based on role-based access will allow that to happen without divulging information that a user wouldn't have in reality. And then finally, the last of the best practices is to be able to export the ground truth data. So the events that were generated, that's the ground truth, the thing, the omniscient picture that the users are trying to derive. And so being able to export that and compare with the data products that exercise participants created allows them to grade how well they did, identify what needs to be improved, which situations they have problems with. Those kinds of things allow the comparison of what was expected and what was actually generated. So following those best practices, we've built up ObsSIM, a system, as I said, we've used for 4 years on many different exercises. And that's been used as the primary simulator for hundreds of customer tests and exercise. And during that process has generated more than 205 million sensor observations. So we're able to generate far more data than the user would have been able to if they designed their exercise by hand or just grabbed historical data for playback. So a significant number of sensor observations, and demonstrably we've seen the time to design SDA test and training exercises decrease from months down to minutes, able to react to changing inputs in real time. The planning of space events in minutes is something we've seen real exercise designers do with this system. So that's all I have. I'll turn it back over to.
All right, well, I'll jump right in, Stephen. This is Danny Brown, everyone. Thank you so very much, Stephen, for that presentation, and all the information is super insightful. We do have a few questions to start. Just a reminder for everyone to be sure to add any questions in the Q&A as you think of them, and we'll attend to those. But to get us started, the first question that came in is, does this ObsSIM run on the cloud, and does AI Solutions own it? I believe it refers back to slide 13 on the design workflow.
So yes, ObsSIM does run in the cloud. It's structured as a set of microservices that run in containers. So it's deployable in a wide variety of environments. So we do have it deployed to the cloud, to public clouds. It's also deployable to private clouds, air-gapped networks, that kind of thing. Yes, we do own it, but the data is yours since it's synthetically generated data. Anything that's created can be exported and kept for training purposes and future exercises, etc., owned by whoever the user is.
Great, thank you. We have one in the Q&A. It says, "Hi, Stephen. Thanks for the presentation. Are the observations generated raw observations or processed sensor data products? For example, images versus astrometric measurements for electro-optical sensors.
So currently we do not simulate the image chips from electro-optical sensors. It is the processed observations, although that is something we are looking at implementing in the future. So it's the processed data that comes out.
Great, thank you. Thank you for the question. Let's see here. Here's another one that came in. Which of the exercise types you talked about would be the best for ObsSIM? And a add-on to that is, could ObsSIM be used to drive a wargaming simulation? You talked about that, I believe, back on slide 8 around tabletop exercises and etc.
Yeah, so definitely ObsSIM provides more capability than you'd see in a tabletop exercise or a just a historical back, because it can respond in real time to input. It gives a lot more power to the exercise designer. Yes, it can support wargaming. In fact, we currently do, and we'll be supporting several war games here in the next 3 months. I think 5 of them. So yeah, it definitely can be used. It has been used for those kinds of exercises, and is able to do that into the future as well.
Fantastic. Appreciate that. Let's see if anyone else has any questions, put it in the Q&A section, please. Might have just gotten another one. We did. How does ObsSIM task sensors to find and select observation opportunities for the modeled event? What sensors are used in this process?
So we have pre-built models for a number of commercial and military sensors. The exact number escapes me right now, but we are modeling well over 10 commercial networks, and then the U.S. Space Surveillance Network. So we're able to do commercial and military, have models for those. And Danny, can you remind me of the first part of that question?
Yeah, it says, how does ObsSIM task sensors to find and select observation opportunities for the modeled event? Okay.
Yeah, we support several different tasking schemes. One of them is a priority list. So, for example, a high rate revisit list, assigning certain targets of interest a priority level with timing constraints put on those. For example, top priority might be things you want to stare at. Second priority might be, revisit every 15 to 30 minutes, that kind of thing. So we support that kind of tasking scheme, as well as optimized tasking for target revisit rates. So each target of interest can be assigned revisit rates, and the system can go in and optimize a plan to track all of those, adhering to constraints like time. We're also one other thing. We're currently adding in the ability to just to do unqueued tasking. So searching and finding without being tipped off or tasked on a certain set of objects, but just scanning the sky.
Great, thank you. We do have another one here. It says, what kind of input parameters can you provide for an RPO event with a breakup or a launch or what have you? I think that refers back to slide 11.
So specifically for an RPO, we support multiple types of RPOs in all different orbit regimes. So, included in that are natural motion circumnavigations and forced motion circumnavigations. So inputs would include the states of the spacecraft involved, timing of ingress, and when the circumnavigation occurs. You'll have things like the standoff distance, lighting constraints. So maybe you want to start the RPO under certain lighting constraints, visible or not visible, or illuminated or not illuminated. For the forced motion navigation, you'll have things like how often to burn to maintain the target standoff distance, things like that. So pretty flexible, a lot of knobs that can be turned, or they can be automated, pull an event off the shelf, an RPO event, for example, off the shelf, and use that.
Sounds fantastic. Looks like we've got one more question. We've got, what kinds of maneuvers or maneuver sequences can be designed in ObsSIM?
So we support a lot of different maneuver types. Besides the larger events like RPOs that are a sequence of maneuvers, we support station keeping, arbitrary impulsive delta Vs, plane changes, orbit raising and lowering, those kinds of things. And all of, as far as the sequences, those more lower level maneuver types are structured in such a way that they can be chained arbitrarily by the user. So you can, for example, launch into an injection orbit, right? And then perform the maneuvers during checkout, and then stitch onto that a raise, an apogee raise into a GTO orbit, and then finally inject into GEO. So they can be added together as building blocks, chained together to form whatever kind of event sequence that you'd want to use.
Fantastic. Well, that's all the questions that we have for now. Thank you so much for answering all of those. If we could go to the next slide, we have a few before you go slides to take care of for those that are on the call with us still. Our next quarterly webinar will be Autonomous Path Planning for Cislunar Trajectory Design. This will be on Wednesday, May 15th from 1 to 2 p.m. Eastern. Our speaker will be our very own Fabio Chiappina. All you have to do is simply scan the QR code on the screen to register to reserve your seat now. Go ahead and do that. If you take out your phones, scan that QR code, that'd be great. Give you just a second. If you want to go to the next slide. So on this one, we'll have our Free Flyer 7.9 release webinar on Wednesday, March 27th from 1 to 2 p.m. Eastern as well. This QR code will take you right to that registration page as well. Open up another window for yourself.
And Danny, just to jump in here a minute, I did drop all of these hard links into the chat as well, which we'll leave open for a few minutes towards the end of the presentation if folks want to take a look at those URLs again.
Awesome. All right, well, let's go on to the next slide, please. So thank you all once again for attending today. We greatly appreciate it. As we mentioned at the beginning, the slides and recording will be sent out within about 24 hours to all attendees. If you have any follow-up questions regarding the material today or Free Flyer in general, Feel free to use the information on the screen to reach out and in the chat that Chris provided as well. Last but not least, have a wonderful morning, afternoon, or evening, depending upon where you are on the planet. And this ends our Q1 AI Solutions webinar for today. Thanks so much for attending. We'll leave this up on the screen for another minute or two. Thank you.